Good morning, everyone. My name is Kuaven Moody. This is Computer Science 131, and in today's presentation, I will be explaining matrices and Sobel edge detection. So, in this presentation, we're going to be going over what matrices are, the types of matrices, what is Sobel edge detection, how do you use Sobel edge detection to find the convolution of an image, the Sobel operator, and our conclusion. So matrices are a set of numbers arranged in rows and columns as as to form a rectangular array. The numbers are called elements or matrices of the matrix. And matrices have a wide application in engineering, physics, economy, statistics, as well as in various branches of mathematics. In this first example, you have the following diagram. It shows rows and columns that are 3 by 2. And then in this next example, we have a diagram that shows rows and columns that is 2 by 4. So we can solve matrices by performing different operations such as addition, subtraction, scalar multiplication, and transpose of matrices. So first we have the addition of matrices. The addition of matrices is one of the basic operations that is performed on matrices. Two or more matrices of the same order can be added by adding the corresponding element of the matrices. Example, we have a 2 by 2 matrix that can only be added of there if there is another 2 by 2 matrix and other dimensions will not work. So we have a 2 by 2 in this first one and a 2 by 2 in the second one. What we're going to do is we're going to add the 4 plus 1, the 8 plus 0, 3 plus 5, and the 7 plus 2, and so and such and such. And they're only allowed to work if they're in a 2 by 2, a 3 by 3, or 4 by 3, not a 2 by 3, 2 by 4. That will not work. Some properties of addition matrices. So similar to the addition of numbers, the matrix addition also has similar properties like commutative law, associative law, additive inverse, and additive identity, and etc. But these four that I've just stated are the four most important ones. So commutative property. If A were to equal A1 and B were to equal B2, are the two matrices of order m times n, then the matrix addition A plus B may equal B plus A, and that is the addition of matrices in the commutative property. Now, in the associative property, if we have A equals A1, and B equals B2, and C equals C2, and there are three matrices of an order m times n, that then your solution will be open brackets A plus B, close brackets, plus C equals A plus open bracket B plus C. That is matrix addition in the associative property. So in the identitive property, if A equals 1 is a matrix of the order m times n, then the additive identity of A is 0 of order m times n, such that A equals 0 equals 0 plus A equals A. That is, the 0 matrix is the identity of matrix addition. Lastly, we have the existence of identitive inverse. So if A1 is a matrix of order m times n, then the additive inverse of A is negative A equals negative A1 of order m times n, such that A plus open bracket negative A close bracket equals 0 equals A plus negative A in brackets. That is the negative A matrix is the identitive inverse of matrix addition. Next, we have subtraction of matrices. So subtraction of matrices is an operation of elements, subtraction of matrices of the same order, that is, matrices that have the same number of rows and columns. For example, here we have a 2 by 3 column, and you can see how they minus the 0 minus the 2, the 1 minus the -6, the 4 minus the 8, the 5 minus the 4, 3 minus the 7, 3 minus the 5, and the 7 minus the 2. And the same thing for the second example. They cannot be they cannot have odd numbers. They must all be the same row. They must all be 2 by 2, 3 by 3, or 4 by 4. They can't be 2 by 3, 3 by 4, or it won't work out. So what is scalar multiplication? The matrix scalar multiplication is the process of multiplying a matrix by a scalar. So let's say we have A being a matrix and K being the scalar, the real number. Then K times A is the result of the matrix scalar multiplication. And to find Ka, we must multiply every element of A by K. So this is our first element, 2. So we're going to multiply everything by 2. So we have 2 times 10, 2 times 6, 2 times 4, and 2 times 3. Example 2 here, we're multiplying everything by 4. So we have 4 times 10, 4 times -9, 4 times -1, 4 times 4, and we get our results. So multiplication of matrix. Matrix multiplication is a binary operation whose output is also a matrix when two matrices are multiplied. In linear algebra, the multiplication of matrices is possibly only when the matrix is compatible. So how do you do that? So right here below, I have easy steps that will make it easy for you to multiply matrices. So step 1 is to make sure that the number of columns in the first matrices is equal the number of rows in the second matrix. Step 2, multiplying the elements of the first row matrix by the elements of the second column in the second matrix and add the products. This element is in the first row and the second row column of the resultant matrix. And then step 3, place the added products in the respective positions. Here are some examples. So we have 4 times 1 times 3 equals, you do 1 times 4, 2 times 4, 3 times 4, you get this. Next we have another 2 by 2. We have the first row being 1 over 1 and 2, 5 and 6. What you're going to do is you're going to do 1 times 5 plus 2 times 7, and then 5 plus 14. These are your results. And the second row is such and such. So properties of matrix multiplication. So there are certain properties of matrix multiplication in linear algebra in mathematics, and these properties are non-commutative, the distributive, and the associative. So the non-commutative matrix multiplication, you use two matrices, A and B, and you would get AB is not equal to BA. In the distributive property, it can be applied while multiplying matrices. Example, A open bracket, B plus C close bracket. It could be A times B plus BC times B times C, given that A, B, and C are all compatible. And the associative property, matrix multiplication is associative given that matrices A, B, and C, such that the products A, B, C, and A open bracket BC are defined as open bracket AB close bracket C equals open bracket equals A open bracket BC close brackets. So how useful are matrices? So matrices have a wide application in engineering, physics, economics, and statistics, as well as in various branches of mathematics. Matrices also have important application in computer graphics, where they have been used to represent rotations and other transformations of images. Matrices in real life are used in um, optic science to account for refraction and reflection. And matrices are also useful in electrical circuits and quantum physics. Moreover, matrices are used to solve AC network equations in electrical circuits. So, next we are going to be asking ourselves, what is the Sobel edge detection? So the Sobel edge detection is an algorithm that works by taking a matrix that is smaller than an input image known as a kernel over every pixel in the input image. And each time the matrix is run over the image, we can measure the change in the gradient within the kernel. And then a greater change in pixel intensity signifies a more significant edge in the image. And this works best on grayscale images. So let's say we have a 2D convolution. Here's our example. So to find the convolution, it's quite simple. You start with a kernel, which is simply a small matrix of ways. This kernel slides over the 2D data input data, performing an elemental wise multiplication, which is a part of the input, and it is currently on, and then summing up the results into a single pixel. So here's an example. We have 2 by 3, and what's going to happen is you're going to multiply everything out. And then, like, notice before that the origin of the image pulse response is always center, which is the h open bracket 0, 0 is located at the center of the sample of the kernel, not the first. So the center is always going to be 0. So what is a Sobel operator? The Sobel operator is an approximation of the derivative of an image. In other words, it would be a discrete derivative. And it is unnecessary to take discrete derivatives in both the x and y direction of an image. So how is it derived? The Sobel operator is to quantify the rate of change of the pixel's intensity throughout the image. In other words, it seeks to calculate the spatial derivative of each pixel in the image. At the boundary between objects and regions in an image, there is usually a rapid shift in pixel intensity. So, conclusion. So these are some in closing and important information on the Sobel operator. So as I've stated before, Sobel operator will only work on grayscale images, and the images also need to be free of noise in order for the Sobel operator to pick up the noises as an edge. And with the example given below, we have a picture with the color pixels, aka noises. And if you were to apply Sobel operator, you would be able to pick up off those noises, like shown below. So, like the images before, if we do have a noisy image, we can apply the Gaussian filter before any processing can be done. And the purpose of this filter is to combat the noise image. So this is what it looks like before, and this is what would happen after you apply the Gaussian filter, which is exactly the Sobel operator, and you would just get the edges of the image. This was my presentation on matrices and Sobel operator. I hope you enjoyed. Thank you.